Well, welcome everybody. Thank you for coming this morning. It's my pleasure to introduce Albert Gatt from the University of Malta. He will give us a interesting and challenging talk about some important issues in the field of natural language generation. In the abstract and the bio, you have when we announce his presentation, you have some details about this talk, about his curriculum. But let me mention that apart of being in the University of Malta, he has strong connections in the Netherlands with the Tilburg University, is it? Where he has making research with some groups over there, and has also very good connections with other NLG groups that are important in this field, like the group in Aberdeen, also Spanish group, like for example the group of Daniel Sanchez in the University of Granada, and he is currently also a member of the board of CiTIUS, which is the special interest group of ACL, which is the Association of Computational Linguists, specifically on natural language generation. So he's a person that has a very wide knowledge about what's going on today in NLG, many perspectives. He told me yesterday that he has a background as a computational linguist, in artificial intelligence, and I'm forgetting something, your master?
Psychology.
And psychology. So he has a very wide interest in research. He knows a lot about not only NLG, but also, of course, artificial intelligence, and lots of related methodologies and techniques. So please feel free to ask him about any aspect you mentioned and enjoy his talk today. So thank you very much, and it's your time, Albert. Thank you.
Thanks, Alberto. Thank you for coming out. Is this mic? Is it sounding okay? Yeah. Okay. When I was preparing this, Alberto suggested that it would be a good idea to start with a bit of an introduction to NLG, natural language generation, and what that's all about. Although I think some of you heard Alejandro's presentation yesterday, and you of course, many of you will know. But what I propose to do is start out with some examples of systems and applications that I've had opportunity to work on. And then I will zoom in on one specific subtask of NLG, which has occupied me for a few years, and talk more about that. And so the way I'm going to approach this is both as a sort of a computer scientist interested in building systems that work, but then when I zoom in on this one task, which is the task of generating referring expressions, I'll also be putting my psycholinguist's hat on and talk a bit more about some experimental work that we've done, as well as the computational modeling. Okay. So where I'm coming from is this field where our starting point is usually some input data, and we're assuming that the input data is not linguistic, right? It could be signals, it could be symbols, it could be the sorts of weather report data that some people here have worked on. One of the perpetrators are sitting in front of me. Or it could be, something more of a more continuous nature, like numerical information sampled at very high frequency. And we want to go from that to text of some kind in some language. And if we do this, the transition from that to that involves a considerable series of transformations, and I'm interested in how that process happens at various stages. So this is a field that has a lot of application domains. A lot of people have used NLG to solve different sorts of problems. The classic, as you know, is weather reporting. So in that case, the data is some weather information, and we're generating a weather report. But I, for example, have worked, and I'll talk a bit more about this, on the generation of medical summaries. So the starting point there would be some data about patients, their health conditions and so on. And the output would be a summary of the sort that a doctor might need to read to be up to speed on what's going on in terms of a patient's condition. But another application, for example, is persuasive text. So, for instance, there's a classic project by Reiter et al. Where they were, again, this is sort of a health application, but the idea was they were working with smokers, and they were trying to create personalized, using user questionnaires. They tried to create personalized letters that would be sent to these smokers regularly to give them some motivation to stop smoking. It didn't work, by the way. They actually had a large this was the evaluation of this system was one of the largest evaluations ever. Hundreds of people, controlled conditions, and so on. Real, evaluation in the wild. And of course, the evaluation measured, what proportion of people actually stopped smoking. Yeah, not many, unfortunately. But Karenini, for example, has also done interesting work here on nothing to do with health this time, but generating arguments to persuade people in favor of certain choices. Like for example, you have an interface that's showing you different housing options, and this is telling you the pros and cons of the different places that you might want to invest your money in to live in. Right. Another application is narrative generation. So people are looking at generating text. Also for entertainment purposes, so generating stories and so on. And finally, an area that I'm beginning to have, over the last year or so, I've started to look at increasingly intensively is image and video description, where the input data is a picture, a photograph, or a video, and the output is a description of that image or video. The range of methods that these approaches cover is vast, and they range from knowledge-based systems to all the way through systems that rely on classifier cascades and up to deep learning. So most work here, for example, on image and video description is now dominated by the deep learning paradigm. I'll come back to that towards the end of this talk. So what I propose to do in what follows is I'll talk about a couple of examples from my own work, and then I'll zoom in on this one task, and I'll try and persuade you that one of the things that's worth doing from a scientific perspective is first of all to kind of it's worth zooming in on one task because from an engineer's perspective you want the system, and that's the first thing I'll talk about. From the scientific perspective, you want to understand what the real problems are. Zooming in is important. But then deploying methods from cognitive psychology, experimental psychology, as well as algorithmic modeling is worthwhile. Okay, and then I'll discuss some of our results on the interaction between the production of referring expressions by humans and vision and attention in humans, and what the implications are for our computational models for the automatic generation of referring expressions. But the big picture first. So here's a very small project. This was one of my students who worked on a small project, relatively small, on where the input data was just a profile of a person on LinkedIn, right? And the idea was that you start from this. And there's stuff in that profile which, in a way, gives you the basic building blocks to tell a story about this person, or generate a biography, essentially. And so what we tried to do in this particular case was, rather than just have a system which reads in that information and maps it to words and sentences and generate the text, well, we had to do that, of course. But the aim here was also to explore variation. So this is one of the big challenges in NLG, is that systems are often quite repetitive. They do things in the same way, given two inputs which are in any for all intents and purposes isomorphic, right? The output is going to look the same. And instead, what we were doing here was we were working with what we call a roulette wheel model, where we had corpus data that from which we derived probabilities of different types of syntactic constructions and lexicalizations. And then instead of having a model which always chooses the most likely outcome, we have a roulette wheel which is biased. So 20% of the time for this kind of structure we generate this kind of sentence, but 40% of the time we generate a different way, and so on. So one of the biographies might look like this. This is a fictional person called Andrew O'Sullivan who's been working at Vodafone Malta since 2012. But we could also say that in this way. Vodafone Malta has been Andrew O'Sullivan's place of work since 2012. And we could also say it in this way. Andrew O'Sullivan has been employed at Vodafone Malta as a senior financial officer since 2012, and so on. The point here is that one of the really intriguing questions to me is that when we produce language, we are not deterministic machines by any stretch of the imagination. And although NLG, like many areas of NLP, is dominated by statistical methods, even those statistical methods do not necessarily capture the variation, because statistical methods, the most common way to use statistical methods is to have probability distributions on the basis of which we can identify the most likely and therefore the best outcome. But there's a different way to use those distributions, which is to actually work with the distribution and make the system non-deterministic in this sense, do different things at different stages. And this is a point I will also come back to later. A second example that I wanted to mention is the baby talk example. This was, I think, one of the biggest data-to-text projects so far, really, in the field. In this case, we were working with a ward, a neonatal intensive care unit, where there's a child over there. It's not easy to see because there's a whole forest of equipment, right? In the neonatal intensive care unit, the child is usually, has health complications. They're usually born quite early, prematurely, 26 weeks, 24 weeks sometimes. And so they have to be kept under constant surveillance and they have constant treatment. And what we were trying to do, because this ward gathers a lot of information about any individual child, and that's very difficult for the personnel, the medical professionals, doctors, nurses, to actually process, right? Because every shift is 12 hours. The amount of information on average for one patient in those 12 hours is roughly 30 to 40 megabytes. They have visualizations, but imagine a doctor joining a new shift or a nurse joining a new shift, right? He's going to have problems processing all of that information. So what we tried to do was take the information that is normally presented in this sort of visual format and generate actual text, in this case in English, where, instead of the doctor having to trace the signal to see what the oxygen saturation, that's SaO2, that's the level of oxygen in the blood, instead of having to trace the signal to see what it's like, the system just says it's variable within the acceptable range, but there have been some desaturations down to 38. I promise you that is a sentence that a doctor can understand. We were, however, in this, I was in this funny situation where, I was mainly responsible here for the actual natural language generation component of the system, and I was designing a system that generated text that I could barely understand, but it was based on expert advice, so at least I was confident that it actually made sense. We also evaluated the system on ward, so we deployed it live and for a few months, and that also gave us some indications about how effective it is. I would like to just go into this system a little bit more and explain what the different components do, rather than just offer you this high-level picture. So this architecture, not surprisingly, the first step in a system like this is that we have to analyze the data. And the data in this case, for example, ranges from, well, there are three main types of data. There's the continuous data. These patients have 8 channels, 8 sensors attached to their person. There's heart rate, blood pressure, oxygen saturation, temperature too. There's central temperature, peripheral temperature. You know, so it's a lot of information which is sampled at a frequency of 1 hertz. So over 12 hours, you can imagine, you know, there's a measurement for each of those 8 channels every second. That's a lot, right? So that's the continuous data, which has to be shoved through a signal processing module that has to identify the trends and patterns there. And then there's what we call sporadic data, which is more like symbolic data, which these doctors and nurses at the cot side, as you saw here, have a monitor, and anything they do to the patient, they record online through the monitor. And so sometimes there's a form. So for example, they've performed this procedure called an intubation. There's a box that they can tick, you know, we did an intubation. So that's recorded as symbolic data in a database. And then there's also these free text boxes where, you know, they just type any interesting records so we had to do some text processing as well to go from that text to extracting the relevant events. Like if somebody types morphine given, we need to, you know, we need the system to figure out that this was an instance of a drug administration event involving morphine, right? And so all of that, once processed, goes into our input knowledge base, which then goes through a phase where we're applying expert rules, reasoning rules, mostly in the form of forward chaining rules, where what that component is trying to do is figure out not only what these events are based on an ontology which we had to construct through consultation with the experts, but also try to do reasoning such as if there's an event of type A and an event of type B, and the distance in time between those two events is less than or equal to some particular threshold, then it's very likely that event A caused event B, for example, right? So you know, later on, shortly after this architecture was designed, I started getting interested in fuzzy reasoning because, as you can imagine, dealing with these sorts of causal and temporal relations, when you have temporal intervals which are themselves uncertain, right? That's a brilliant sort of case for trying to work with this in a fuzzy way. And finally, after all of that, we do the actual language generation proper, where first we select what to say. So you have to imagine that this is over a 12-hour shift. The number of events identified after these initial steps is in the thousands, right? And no summary can report thousands of events. Also because most of those events will not be so interesting. Yeah? Because, you know, if you keep telling the doctor that the heart rate is normal, you know, the doctor doesn't really want to hear that, right? The doctor's only interested in when the heart rate stops being normal, because then she has to do something about it, right? So anyway, document planning is the phase where the system selects what to say and also determines the structure, how to say it. And then microplanning and realization is where we turn that into actual text. So just to give you a flavor step by step, let's say we start from this piece of data here. That's a heart rate signal, a real one. It's an actual example from an actual data set. And you'll notice that the heart rate is you know, pretty stable, but then suddenly we get these spikes going down. Yeah. Now some of that is noise. Okay, some of that is noise because, you know, the patient moves, the sensor falls off or shifts, right? But some of it is not noise, and so our signal processing module would hopefully identify that, and it out of all these spikes, it actually determines that there are 6 cases of what we call bradycardia events. A bradycardia is a sudden drop in heart rate. Okay, so this is a condition where the heart rate suddenly really drops, but for a very short period of time, sometimes in the order of a second or even less. Well, not less. It's in the order of seconds. And so 6 of these have been identified, and they've also been labeled heuristically using expert rules with an importance value. How important is this event for a nurse or a doctor to know about? Well, not all of them are important, right? You see that some of them have importance levels above 70, but 3 others are quite small bradycardias, so not so important, in the order of 30. Importance ranges from 1 to 100. So that's the phase where we've interpreted this raw data and come up with a sort of list of events that the system can actually process. Each of these events covers a temporal interval. And then from that, we choose 3. We choose only the 3 important ones, 1, 2, 3. And the document planner selects those 3 and decides on how they should be reported. And these are reported, in this case, in something called a temporal sequence. Okay, so basically what we're going to do with the report is we're going to mention that there was a sequence of bradycardias happening one after the other. Okay, that's what that means. So that's the document planning stage. At the 3rd stage, the microplanning stage, we want to turn that into something, we want to transform that into something that is closer and closer to actual language. And so the first thing we need to do is come up, this is the microplanner, it's got to come up with a semantic representation. Okay? And the semantic representation contains information about how this information should be expressed. So in this case, this is an event. The microplanner determines that this is an event which should be expressed using an existential construction, which basically means that we don't say, for example, a bradycardia happened. We say there was a bradycardia. That's an existential sentence, okay? Because that's how it should be mentioned in the report. The tense is past, so we're moving very close to language now, okay? We're no longer working with raw timestamps. We just now work with actual tense. This is past tense, yeah, because it happened this morning, not now. And this is an event which will be expressed with the verb to be. There was, and it has 2 arguments, the bradycardia and the numerical value of that bradycardia. But in fact, there are 3 of these, and part of this process is that the system actually maps each of those 3 into this representation, but then it aggregates them into one, so as to make the text more readable and concise. And at the end, sorry, some of this is falling off the screen because I prepared these on a different software, so I apologize for that. But ultimately, we're going to go from this to a sentence which is going to say, this is the realization stage, and we're going to say there were 3 successive bradycardias down to 69. Okay, so from that signal, we end up with that sentence. Now you've got to imagine this for a much larger set of data. This is one fragment of an actual report. Okay, this is what the report actually looks like. One section of the report. The reports were usually in the order of 2 to 3 pages of text. Okay. Not bedtime reading, of course, but okay. That's by way of an introduction to what happens in natural language generation. And I thought I'd give you 2 examples, because the first one illustrates this problem of non-determinism, like variation, as we had with the LinkedIn biographies. And the second one gives you a flavor of just how complex the whole process can be as you go from non-linguistic data to actual text, in this case, in English. To my mind, there's a lot of important research issues in NLG, but some of the ones that have intrigued me a lot over the past years are the following. One is, of course, the choice problem. So given your communicative goal, which might be to persuade somebody to stop smoking or simply to give information to a doctor about their patient, yeah? Given all the information you have available, what do you choose to say? Because you cannot say everything, right? And humans are really good at this. We are very good heuristic machines. Given a context and given a goal and given, given our interlocutor, the person we're talking to, we seem to find it very easy to effortlessly decide what's relevant, right? in a given context. Modeling that in a system is quite hard. A second question is that has to do with the presentation problem. And by presentation here, I don't just mean, things like layout, although that's important, or the combination of text and graphics, which is also important, but also the language itself. What is the structure that we are going to give information in? What comes first, what comes last in a text? In the medical summary I showed you, you might have noticed that what comes first is in the report is not what comes first in time. Okay, the report is not chronological. In fact, if you look at the report, it shifts wildly in time, backwards and forwards all the time, because what the system's trying to do is structure based on importance. Put the most important things first, and then relate everything to those things. Yeah. So there's a presentation problem. The other issue that is very intriguing is how do you turn information into a narrative? And by narrative, I don't just mean something entertaining like a story you read in a book, but by narrative I simply mean a text, a piece of language, a linguistic artifact which contains events but also contains linkage between those events that allows the reader to infer causality and other processes. Okay, so there's that's what I call the presentation problem. What's the structure in the data, and how do you convey that structure? The third class of problems is the noise or uncertainty problem. A lot of the data contains uncertainty. When we find bradycardias in a signal, that's a guess that the system makes. When we say that event A causes event B, that is also a guess that the system is making. Yeah, the temporal intervals we work with are uncertain. The beginning and the end points of an event are actually, themselves fuzzy intervals, right? So how do we handle uncertainty in the data? How do we handle noise in the data, including spurious stuff that we shouldn't pay attention to? And what noise is, I think, depends on the task, right? So if I was asked to give a description of this room right now, if all I was asked to do was to identify the room, I'd probably just say it's a lecture room, or, and that's it, right? I wouldn't need to say how many people are in this room or who is in this room. But for a different purpose, for example, because I'm being interrogated by a police officer, because somebody's laptop was stolen, right? I would have to identify the people in this room. I won't. I can't. I don't even know you. You see, but my point is, what is noise depends on what you're doing, right? Things aren't noise just because, they're not noise in and of themselves. And finally, a really interesting problem for me is the grounding problem. So what is the relationship, in fact, between language and the world, and how do linguistic expressions, how are they rooted in the world? And so what I propose to do now is take a step back and look at some of these problems. I can't look at all of them. And look at them from two perspectives. One is the computational perspective. As engineers, as computer scientists, we're interested in what methods work, what algorithms are effective, how can we make the algorithms efficient, how can we optimize our processes, etc. And then there's the question of, what kind of system do we want? Do we want a system which is human-like? And does that mean we want the output to be the sort of output that a human might produce? So I'd love it if my system was indistinguishable from a human being, right? That would be cool. Or do I also want human likeness of process? So do I want my system to process information the way humans process it? That's a more subtle question, right? But there's so that's one class of one perspective for looking at these four main questions that I pointed out. Another perspective is the cognitive perspective. So can we learn anything by looking at what humans do carefully, experimentally? And can we also think of our computational models as testable models of how humans produce language? Okay, and depending on what you're doing and why, you might be interested in looking at things from the computational perspective only, or the cognitive perspective only, or both, right? Depends what you're trying to achieve. Well, from here on in, I'm going to zoom in on the microplanning task. And I'll talk specifically about some of our research on one aspect of microplanning. And I'll try to look at it both from the computational and the cognitive perspective. And in the process, I'll answer, well, I won't answer. I'll give some indication of how we're dealing with those four problems that those four questions that I mentioned. Microplanning, just to remind you, is that process where the non-linguistic information which has been selected, gets mapped to linguistic or pre-linguistic structures. Okay, so among other things, over here we have to use words. So that's where our system, having found the bradycardias, actually decides that to express these, it has to use the verb be, but in the past tense. So they're where, things like that. The other is aggregation. So you saw an example of that. We had 3 bradycardias, but the system decided to express them in one sentence. It merged them. And a referring expression generation, which didn't really come up in the baby talk example much. How do you describe a thing? So no text is ever about nothing, right? Texts are always about something. And if you're talking about a person or an event, you have to figure out how to describe it. And typically, there's a lot of information you can say about a thing. What are the things you should say? And that's, in fact, the one that I'd like to zoom in on, because that's also an area that I've been doing quite a bit of research in over the past decade or so. So from now on, right, from this picture, I'm just going to zoom in on this one problem, which is referring expression generation, and look at algorithms for that. And specifically, this is happening somewhere along the transformation from from data to text. Somewhere along the way, we have to have this bit in microplanning which decides what to say about individual things. And to make the problem more manageable and more amenable to experimental study, we often have worked with reference in visual domains. So we're interested in the problem where, given a set of objects like what I show you here, right, we want to identify one of the objects. We want to generate a definite description, a noun phrase, which will describe this object, for example, unambiguously. So I could just say the one in the middle, or I could say, the red one facing to the right, but it wouldn't make it wouldn't be enough for me to say the red one, because that wouldn't identify the object. There's another red one over there, so it's still ambiguous, right? So this is a sort of small zooming in onto a small problem scenario, which hopefully we hoped would give us a handle on some of these broader questions, and we decided to explore that in more detail. Okay, so the issue is how we describe objects in order to distinguish them from other objects, and I'm going to assume that this is happening in a visual context. And what I'll do is I'll compare some computational and cognitive models, and the aim here is to understand both how humans process visual information and how we can model that using systems. By the way, what's the usual procedure here? Do questions come at the end, or? Usually at the end. Okay, so in this particular case, right, zooming in on this particular case, the 4 problems that I mentioned at the beginning take on a specific, I was going to say value, take on a specific character. The choice problem in referring expression generation is, given all the properties of an object, which ones are to be mentioned, right, in the description. The presentation problem becomes a problem of choosing exactly how to refer. I could use a pronoun, but I can only use a pronoun really if the object's been mentioned before. Otherwise, if I say it, you don't know what I'm talking about, right? So I might use a definite description instead. The noise or uncertainty problem is a sort of the quite realistic problem of deciding what attributes actually are. So, colors are not crisp properties, right? They're usually on a continuum, depending on your model of your color space, and you know, I will here simplify by assuming we know what the properties are, but in fact that's a very real problem. And finally, the grounding problem, which is, you know, how are these visual properties of objects that we talk about, where do they come from? How do we figure out, you know, what aspects of the visual scenario translates into what linguistic properties that we can actually mention in our descriptions? Okay, so this is going to be the topic from now on. And we're kind of thinking along these lines. So let's start with the choice problem. Okay, there's a couple of algorithms, in fact, a class of algorithms which are sort of classics. And in our research, we thought, let's start from those and see how far we can take them and what they need to be improved. Okay. So given a scenario like this, where we have an object we want to distinguish from some other objects, sometimes we call the other objects distractors, yeah? And let's assume that we know what the properties of the objects are. The first problem we have is to decide which of those properties to mention, right? And one interesting question here, remember I'm kind of treading both a computational and a cognitive perspective on this problem, right? One of the questions is, what are the constraints under which speakers actually choose what to say? So if we're able to answer this question, we might be able to make our algorithms more human-like. And the second is of course, how do we then interpret those constraints into computational models that actually work? Well, depending on who you ask, people will give you a different reply to the question of what motivates speaker choices. Yeah, one class of answers harks back to classic pragmatic theory, where you have people like Grice, H. Paul Grice, and other people in relevance theory and so on, who came up with some principles that speakers appear to observe when they speak. And one of those principles is whatever, given the purpose of your exchange, right? Given the purpose for which you're producing language, don't say more than you must. Okay, so don't give extra information. So in this case, if the purpose is to just identify the object, right? Then what I should do is I should look at the properties of this object and identify the ones that are going to help me distinguish it, and only use those. No extra information, because the extra information would give rise to false implicatures. That's sort of a classic perspective that comes from pragmatic theory. More recently, we've had probabilistic, stochastic models based on utility, which are sort of coming to the same conclusion. Many of these models, by the way, are couched in a Bayesian framework. Okay, and they're arriving at the same conclusion by saying, well, okay, it's not that we don't want to say more than we must, but it's that we want to make life as easy as possible for the person who's reading or listening to this. And so we'll only give them exactly the information that they need to identify the thing we have in mind. Because remember, the problem here is I have an object in mind, you don't know what it is, I have to describe it to you so you know what it is, right? And some of these models, many of these models have taken a Bayesian flavor, some of them are game theoretic. But essentially, under these assumptions, if any of this is true, right, what our hypothetical speaker would say to distinguish this object is the sofa facing right, because facing right is the one distinguishing feature that will distinguish the sofa, right? On the other hand, there's a different class of results, and this is based on some very robust findings in psycholinguistics and experiments on language production, where we don't really just think about utility or the Gricean maxims, but we're interested more in the heuristic behavior of human beings. And one of the things we find, in fact, is that human beings aren't so great at estimating utility or at saying no more than they must. There are things which are just so salient that people use them anyway. So I don't know what you think, but when we run experiments asking people, here's a scenario, describe that object for me, they will use facing right because, they have to, right? But they'll also say red. So most people will say the red sofa facing right. And the reason is that, well, he should be facing that way, right? Or is that a she? No, yeah, they're the same. They're genderless. The reason why people use color, for example, is that color seems to be a very salient property. Okay? When people are asked to describe objects, at least inanimate objects, artifacts like this, the color will be a prominent thing. This also extends to, for example, describing people when you're trying to identify a person, and suppose somebody asks you, who's Alberto in this room? Well, maybe the easiest way for me to identify would be, sorry to use you as an example, would be to mention the color of his clothing, if that would help to distinguish, or mention where he's sitting. The point is, some attributes are salient, okay? And of course, this will depend on the task, but I'll come back to that later. Okay, so those are three stories about what motivates speaker choices, based on a vast literature in this area. If we want to discriminate an object, so identify it from all the others, then maybe we might want to take this Gricean or utility-based perspective, and just don't give extra information. There's an algorithm that does that. One of the algorithms, it's called the greedy algorithm, courtesy of Robert Dale from quite a long time ago. But it has been influential and has morphed into many variants since then. I'll just give you kind of an overview of the classic. If we imagine that our domain consists of three entities, as you see here, and each entity has attributes, in this case the type, the color, and the orientation. Yeah? Now what the greedy algorithm will do, and let's suppose E2, the second entity, is the one we want to identify. What the greedy algorithm will do is it will compare these attributes, and it will compute their discriminatory value. So, that's easy enough. Just look at each attribute. For example, red will discriminate E2 from E1, but not from E3. But right will discriminate E2 from both E1 and E3, right? And then that gives us an ordering of orientation having a higher discriminatory value than color. And we choose orientation, and that excludes E1 and E3, and we're done. Right? So this would be the sofa facing right. If, on the other hand, we take seriously the idea that humans are, have these heuristic preferences, they're guided by salience and so on, then we might take seriously the idea that people might prefer to say the red sofa facing right. Okay? These are sort of what some psychologists call fast and frugal heuristics. People don't compute discriminatory power, they just go by what's salient, right? They use sort of fast and frugal methods, quick methods to find a solution. In that case, some attributes are more preferred than others, more salient. So color might be more salient than orientation. Plenty of evidence for that. For example, because color is often used in situations like this when it's not required, but people use it anyway. So now we have a different algorithm, again, courtesy of Dale and Reiter this time, where we know that we don't do any computation of discriminatory power. We just choose color first. And color excludes E1, but we're still not done because we haven't excluded E3. So orientation is what I have, so we use that. That removes E3, and now we're done. And so the output here will be the red sofa facing right, which is an over-specified description. It contains more information than strictly needed. Okay? Right. In general, what all these algorithms have in common is that they work like this. You can model this process, whether you're doing greedy algorithm or incremental, whether you're doing discriminatory power or salience. The algorithm works kind of like this, where you've got this. You can model it using a loop, where you're just looking at how many distractors you have left. We start with 2, but with each loop, we're going to exclude more distractors. We select a property, and that property might be selected based on discriminatory power or based on salience or whatever. And if it excludes some distractors, we add it to the description and remove the distractors. We've updated the distractor set, and then we're back at the beginning. So this is the general schema for the algorithms. Okay, question one. How realistic are these models? One of the problems with these algorithms is that they're completely deterministic, right? Given the same input, they'll give you the same output. And even stochastic models, such as the utility-based and Bayesian models I mentioned, will have the same problem, because they will compute the most likely or the most useful outcome, solution, and they will always give you that for the same input, right? Whereas humans are not. Humans are very fickle. They do some things very often, but they also do many other things less often, right? So if we think of these algorithms, one of the issues is their determinism, which is a problem if we want algorithms to be human-like. The other is that these algorithms model referring expression generation as a search. Yeah, they model referring expression generation as a search, but maybe and the search is based on searching through the attributes. But maybe that's not what humans do. So what I'll do next is I'll describe two sets of experiments and their algorithmic implications. One set looked at the problem of determinism, and the other one looked at this other problem of search. Okay, so let's start with the determinism. Well, we've run several experiments on refining expression generation. Experiments are very different from using corpora. Okay, when we do corpus-based machine learning work, we have huge corpora, and we have we've done some feature engineering, or we're using deep learning, and hopefully we learn a model that does something useful. In this case, we're very careful about the design of the experiments, and we want to compare conditions. So we keep it simple. What we did in these experiments is we showed people, we put people in scenarios where they were actually talking to somebody, and they were playing a game, and they had each time they were shown a set of pictures, and there was always one picture which had to be identified. Now, in this case, the picture is in the middle, but the object wasn't always in the middle. Okay, so there was an object they had to identify, and we set it up so that sometimes color alone was enough. So here you say the green light bulb, and that's enough. Sometimes size alone is enough, so the large light bulb is enough, right? And sometimes you need either one or the other. So green will do, large will do. Yeah. And what we did was we got people to have these play these games with a partner. They were describing an object, and then the partner would have to guess which one was intended. Okay. And what we did then was we counted the use of attributes and so on, the use of the color or size attributes that people used under these different conditions. So let's look at the results. This slide has okay, there were axes and they've disappeared. Let me reconstruct this for you. Imagine this going from 0 to 100%. Yeah. These are the three conditions. This is the condition where size only is enough. That's this one. This is the condition where color only is enough. That's this one. And this is the condition where either or will do. Okay. That's this one. The blue bar is the proportion of descriptions produced by people which contain only color. That's the dark blue. The light blue is the proportion of descriptions which contain only size, so the large. And the yellow is where they contain both, the large red, for example. Yeah. And it's easy to see that in the size, in a condition where size will be enough, yeah, people produce size and color most of the time. So they're adding color even though it's not necessary. And one of the reasons is that size is usually not selected early in the selection process, because computing size requires comparison, and that takes work. Okay, and heuristically people just use the salient stuff first and then they do the more difficult stuff later if they have to. Whereas here, the picture is very different. Nearly 100% of people use color-only descriptions. And here, where either color or size will work, most people either use color-only or size and color together. Okay, what can we make of these results? So there's obviously a very clear color preference, and size is only used if absolutely required, which means that this algorithm, the incremental algorithm, should be a good one, right? It should be quite good at modeling what people do, because it is playing with these preferences. Okay, here I have color and orientation instead of size, but you know, it's the same idea. The problem though is that these are the results, and this is what the incremental algorithm would do, right? The incremental algorithm, being deterministic, always does the same thing 100% of the time. And as I said before, human brains don't do that. And nor do they just compute the most likely thing and output that. Humans exhibit variation. It's not a uniform distribution. Not everything is equally likely, but there is a distribution, right? And brains don't care about frequencies and probabilities. They care about probability distributions. Okay, well, we thought one way to get past this is to go for a stochastic model, but a stochastic model which forces us to think about what is it that makes people do more of something more of the time. So some clear preferences that can't be ignored, but also do it differently from time to time. And we'd like a model, therefore, which is like that roulette wheel that I mentioned at the beginning, but which actually has a sort of stochastic variation. We call this the probabilistic referential overspecification model, and I'll skip directly to the graphical illustration. If these are the three conditions in our experiment, of course this is one instantiation for these scenarios. These are the three conditions of our experiment, where color only will be enough, or you need both color and size, or you need either color or size, or you need size only. Okay, and what you see on the arcs, so it's a bit like a decision tree, right? What you see on the arcs are probabilities, where it's simply a question of there are two parameters, x and y, and x is a probability of selecting some attribute. So the other attribute is selected with probability 1 minus x. Of course, if we have three attributes, we'd have to kind of unpack those probabilities, but that's easy. Y, on the other hand, is a parameter which models something we call overspecification eagerness, which is how willing is this speaker to allow extra information to come into their description. Okay? And the essential thing here is that we are probabilistically traversing a path where at every point we're making a choice depending on the input, depending on the choices available, but also depending on how we can continue after every stage. So after if color does the trick, sometimes I want to add size and sometimes not. Okay, which is kind of what we see here, right? Where when color only does the trick, there's a small proportion of the time that people do add size anyway. Okay, these parameters were obtained by cross-validation on a portion of our experimental data. Okay, x, as I said, is a probability of selecting some attribute, so the probability of selecting the other attribute is 1 minus x, if we have two attributes. Y is what I called overspecification eagerness, and that actually could be thought of as the task requirements. Okay, so for example, the likelihood with which people add extra information depends a little bit on whether you're just describing something or whether your task is a bit more demanding, like you're giving instructions. You really want to make sure somebody doesn't get it wrong. We have empirical evidence that people add more information depending on the task. So that Y parameter is intended to model that. here are the results. These are the actual distributions we observe. These are the predictions of the model. Unfortunately, you can't see the axes. They're not, of course, perfect, but they're pretty close in terms of the distribution, the shape of the probability distribution for any one of these outcomes is quite close to what we actually observe. Okay. Am I okay for time? How much? Do I have another 10 minutes, maybe? Yeah. Talking time? Yeah. So that was kind of about choices and the fact that speakers, you know, when they choose how to describe objects, there's an interplay between, you know, what's discriminatory and what's salient and fast and easy to use. And deterministic models just won't cut it. What I mentioned earlier, though, is that it's not just about non-determinism. It's also about how do we determine what is salient? How does this actually work in terms of how we see things? So at this point, we began to ask questions about vision and attention, and that's that's the next thing. So imagine I'm asking you now not to describe something, but to find it. Okay, so I show you some scenarios like this, and I ask you to find the red bell in this scenario. That's really easy, right? Because it's the only red thing. Or find the large bell in this scenario. That's probably also kind of easy, although maybe not as easy as this. Here, if I ask you to find the large red bell, that's a little bit more difficult. Now that's search, that's visual search, and that's actually a paradigm which is a very long-standing in the psychology of perception. People do these visual search experiments, and one of the things they do is they vary how complex or cluttered the domain is. So, you know, that can get more and more cluttered, right? And one of the findings here is that if you ask people, as we do here or here, to find an object based on one attribute, the number of other objects seems not to matter. Okay? So you get if this is your how many objects there are, the distractors, and this is the number of the amount of time it takes to actually find the object, yeah? The curve is relatively stable. Okay? Whereas with two properties it's going to be much steeper. This is also a prediction that those algorithms for referring expression generation also make, because when there's only one salient property and it's enough to describe an object, the incremental algorithm, for example, will just choose that. It will check if the property excludes some distractors. So it has to do some comparison against the distractors. So we do see the prediction is that this will take a bit longer, right? The more distractors there are, but it won't take as long as when there are two properties, because then you've got that big while loop and you're doing that twice, right? In the vision literature, the way this is modeled, this phenomenon is modeled is an early model is that you've got these bottom-up processes where you compute the salience of objects. You build a saliency map, which is just a map, a spatial map, in fact, where parts of the visual scene are more salient than others based on how contrastive their attributes are. And we get these pop-out effects. So if this is the only red thing among a lot of blue things, that's going to pop out. If this is the only large thing among a lot of small things, that's going to pop out. And then, you know, if you need to identify something like this, where you have two attributes, you can't do this like this, because these are just parallel processes that don't talk to each other. You need a top-down process which does conjunctions. Okay, so that's going to be slower. And that's why in these models, the observation is that when you have a search based on one property, it's going to be really fast, and it doesn't matter how many distractors there are. This is visual search. Yeah. A more recent view of the same idea is that, in fact, you don't have a distinction between top-down and bottom-up processes. You just have a continuum from very efficient to inefficient search, which is facilitated by things like salience and you're deploying your visual attention to different degrees. Okay, so notice that I've now taken a slight deviation. Yeah, I've started talking about models of visual search and attention, and now I'm going to try to go back to how those might speak to our models for referring expression generation. In these models, as just to remind you, when there's only one property to, and you're trying to find the red bell or find the large bell, the domain size by time curve is relatively flat. Whereas with two properties, it takes you a long time because you have to find a conjunction of properties. Okay, I'll skip this and go right to this. Why is that interesting? Remember, my original question was, we know that people use preference or salience-based heuristics when they describe objects, right? But what is salience? What is preference? Well, of course, there are differences between the visual search task and the reference production task. In the visual search task, what you're telling people is find this. So it's as if you're giving them a template, like a red bell or a red vertical thing, and you're asking them to go and search for something that matches that template. Yeah. In reference production, it's object-driven. You know what you want to talk about, and you're going to look through the sets of properties, if you model it as a search, that distinguish that object. On the other hand, there are some similarities. For example, the role of distractors in visual search is that in some cases, the more distractors you have, the more difficult the search is. And in reference production, that's also true, right? So this becomes more efficient if the properties that distinguish the object are very salient, and if the domain is not too cluttered, and similarly here. So there are similarities and there are differences. Now, one question is, there's a big literature here which has given us insight into what counts as salient and what makes search efficient. Does that in any way speak to what we observe in reference production? Well, once again, we did an experiment where we varied. Now, again, we have three conditions. Actually, there are two separate experiments here. One is an experiment in which people, again, have to describe objects to another person. And in some scenarios, size alone is enough. Okay, so saying the large red bell here will distinguish this from all the other bells. Saying over here it won't. You need both color and size. And then in the second experiment, we had color and color and size. Now remember, we already know that color is more highly preferred than size, right? And what we're doing is we're comparing both of those to this condition in the two experiments. What we're measuring here, though, is speed. We're measuring speech onset time. Okay, so this was a sort of voice-triggered experiment in which when people were shown a scenario, they knew they had to describe this object, and we measured how long it took them to actually start speaking, which is the time, if you like, that it takes to plan what you're going to say. Okay, so this is usually in the order of milliseconds, a few 100 milliseconds or 1,000. I'll skip this and go right here. This is what you see here is in fact the speech onset time, and what you see here is the size of the domain, how many objects there are, 2, 4, 6, or 8. Sorry, 2, 4, 8, or 16. Okay, so this is an example with 8 distractors. Yeah, and the dark bar, the dark line, is the size only condition, and the light line is the size and color condition. And with the exception of this anomaly here, these are just the standard error. Okay, this is the mean onset time across those conditions, and what you can see is that in both of these conditions, the amount of time people take to produce a description is increasing as a function of the number of distractors in the domain. Yeah, so that's some evidence that when people are formulating their descriptions, they're spending time planning, comparing the target they want to describe with the distractors, and the more distractors there are, the longer this takes. Yeah, and of course, in the case where they use two properties, yeah, this is taking longer overall as well. So think of that algorithm again. There's a loop. Yeah? Well, this is where we compare size with color and size. But now look what happens when we compare color with color and size. In this case, the size of the domain, whether you're comparing your target to 2, 4, 8, or 16 distractors, makes no difference at all. In fact, it even goes down a bit, but that's not statistically significant. Yeah? Whereas with this condition, we observe the same upward curve. Right? I'll skip this again. Because, if we now think about these algorithms for referring expression generation and their predictions, they make these predictions. Speech onset time should increase as you need more to add more information. 1 property, 2 properties, 3 properties. And yeah, we find some evidence that that's the case. Yeah. But the other prediction is that speech onset time will increase as domain size increases. Because every time you choose a property, this algorithm compares that property to the other distractors. If you're comparing to 2, 8, 16, that's going to take more time. What we actually find, though, is that that's true for gradable properties like size, but it's not true for salient properties like color. Okay? So what that suggests is that there is a search going on, but it's not quite what these algorithms are making it out to be. Okay? This is the algorithm, again, the algorithm schema. What seems to be happening in this bit here, where we're selecting a property, is that there's selection of, and there is comparison, but it depends on the property. So what does this imply? I think what it implies is that, first of all, we should abandon this crisp distinction between preferred properties or salient properties and dispreferred or non-salient properties. And let's talk instead, because, after all, under different conditions, even size can become salient. Imagine comparing something which is really huge with something really tiny. Yeah? We have evidence that that is also true. Yeah? Whereas color can become less salient. For example, if you're comparing something which is dark blue with something which is a slightly less dark blue, then the color is not so salient, right? So let's abandon that distinction. That's what these results are suggesting. Let's also abandon this idea that we're always working with crisp features and attributes, and let's take seriously this idea that there's a continuum of features of varying salience. And maybe the model we need is a model which, just like the more recent models of visual search, is a model where we have a continuum between selection without comparison. Something is so salient, you don't need to do any comparison. You know that it's relevant, right? Just by looking at this room, I know that that's the only yellow door in the room. I don't need to compare it to every other object in the room, right? But sometimes I will need to, because the differences are too subtle. The saliency is not so high. And of course, there are visual features, and their salience will affect where on this continuum we are. But there's one single search process where how much comparison we do depends on some early stage in which we measure we estimate the contrastiveness of things. Well, I'm running out of time, so I'll just say a few words at the end about where this work has taken us, and why, by zooming in on this one small area of NLG and looking at it both from a psychological and a computational perspective, we maybe can begin to learn more about addressing those problems. I'll skip this and go straight here. One of the issues that we've not dealt with, because we've always thought in terms of search and in terms of features, is that how people search and what people choose to say depends not only on the bottom-up properties of the scene, but also on the top-down knowledge of the scene. And there are some interesting computational models of attention which have managed to model this quite successfully, predicting what's going to be salient based on what kind of scene you're looking at, right? And salience, I think, depends on context and knowledge. So I think we're close to a story about how the selection can work in a bottom-up fashion, but we need the top-down as well. And I've no idea how to factor that in yet. But that's kind of the future. So I've shown you a lot of examples of scenes with bells, but imagine doing this in the real world, right? where you might have this is somebody who manufactures bells. How do you identify that bell over there, right? What are the salient properties of that bell? Or here, what are the salient properties of this bell? Or here, which is much closer to the real world context in which we normally see bells, right? What are the salient properties of any of these bells, right? How do your choices will change just because now the object is in context. And as I said, there are, I won't go into details here, but there are these really interesting visual attention models where, based on a real world scene, saliency is computed from features, but also with global biases or priors. And as a result, the feature-based saliency map will change. So that if you're looking at a street scene, what is salient in the street scene is not only dependent on the contrastive salient features in the street scene, but also the fact that it's a street scene. So some aspects of the scene are just more relevant than others, okay, because it's a street. So by way of conclusion, I've kind of addressed these. At the beginning, I said there are these 4 big questions, and I've tried to show you how we've begun to address them based not only on our experience with engineering hopefully useful NLG systems, but also zooming in on tiny tasks and trying to look at them really in detail. The question I'm often asked is, or we often ask is, do we want to do NLG or do we want to look at human language production? And I want to do both. I want to look at both because I'm interested in both. But my main argument is that to answer certain questions, you need both perspectives. And experiments are useful because they help you to really control things very carefully and make comparisons in a very precise way. Algorithms are useful because, unlike psychological models, algorithms have to be very, very specified at a very fine-grained level of detail. You can't implement a flowchart. You have to implement things with all the parameters in place, right? And systems, real-world applications, are useful because then they also shed light on what is actually working. So I'll stop here, and I won't even go into that. And I'll shut up. These are just some of the people who have collaborated on various aspects of these things I've been talking to you about. I'm happy to answer any questions.
Is it okay? Yes. So thank you very much, Albert, for for this talk. And I'm very happy to see here, for example, in some of the examples you bring this ICG processing, these temporal relationships, which is are some topics that many people here in the past and now in the present have been working for a very, very long time. So maybe one of these peoples can have some question for you. Any? Please.
Thank you very much for your presentation. It's very nice. I have now a question. It's just maybe a suggestion or a comment. It's about how an object can be, or how a property can be salient in an object. I think that there is another. It's not just a question of knowledge and context, but there is something which is quite specific, which is the function of an object. Yeah. And for instance, the color of this pen. This pen is green, maybe, but if you know that this pen is, the writing of this pen is blue, the color is blue. So, okay. And the function, sometimes, even for the question if it's the color or the size, the more prominent, the more salient. It depends on the function sometimes of the object. For instance, for a rope, the size is more prominent. Even probably people would say all the time if it's smaller or larger. So I think the function is a key question also in this.
I agree. So take a real world picture like this. Again, even the type of thing you're talking about will determine what becomes salient, right? So maybe somebody's skin color is not important unless you're discussing things in a political context, for example. Well, in the case of the pen, or the other classic example is the red apple, right? What's a red apple? Is an apple with a little green patch still a red apple, right? Depends on, yeah. One of the ways in which I'm hoping to approach this, I didn't have time to go into this before, is to we are doing a lot of work right now on image description, okay? And typically we start out from real images, and we're trying to generate descriptions like this. This is a description actually from a corpus, okay? But our systems can match this quite nicely, and the way that most systems in this field now work is using deep learning. We have a convolutional neural net to represent the image features, and we have some kind of recurrent neural network to generate on a word-by-word basis with a softmax function to give us the distribution, probability distribution of the words, and hopefully out comes a good description. But what this doesn't do at all is it doesn't take into account any scene semantics beyond the features. And what I would like is to try and first of all look inside and ask, okay, suppose I want now not just to describe the image, but to describe the one of the people in the image. Yeah. Maybe the way I describe that will depend not only on the features of the person, for example, the fact that she's on the left or something like that, but also on the type of scene. And one of the big questions for me is how can we factor these more semantic, more high-level issues into this sort of very feature-based processing which you get with convnets and RNNs. The other element of this which intrigues me a lot is not only function. I agree fully with you that function makes a big difference. The pen's function is to write with, but if a pen is used as a murder weapon, then you're going to describe it differently again, right? I assure you, I have no interest in weapons, but it's the first example that sprang to mind. Function is one thing, expectations are another. So our knowledge of a scene, right, will mean that we expect a scene to be in a certain way. If something changes, deviates from our expectations, then that is exactly what's going to be salient, because it deviates from the expectations. Yeah. Similarly, in the baby talk example that I showed you, I mean, in a way, what we were trying to model there was this idea, right? You have a signal, but if the signal looks, perfectly normal, then there's nothing interesting about it. As soon as it starts to deviate, that's where it's interesting. That's where I want my system to actually say, look, look here. There's a bradycardia, right? So function, scene semantics, expectations, all of these things somehow have to be factored into this work. So.
Okay, thank you. Any other question?
Thank you very much for your talk. Very interesting. Only a curiosity. My question is, if you know speech act theory, if you think that it can play some role in human language production or not, or is
okay. When you say play a role in human language production, do you mean is there any evidence that the predictions of speech act theory play out?
The idea of illocutionary force or something like that can be relevant.
Yeah. So my answer is certainly yes, from an NLG perspective. I could mention a lot of examples where in actual systems, including especially dialogue systems, where you have interaction and the system is generating, but in the context of a dialogue. Many of those systems are founded on some ideas which ultimately are rooted in speech act theory. Okay. Also because they need, a system needs to try and understand some of the implicatures in somebody's utterance in order to generate the appropriate next utterance. And there's even though you won't find perhaps a specific module that says that defines things according to Searle's schema, it is nevertheless founded on ideas that ultimately come from there. Much of the work in referring expression generation has also been influenced by speech act theory. The problem with speech act theory, though, when you take it more to the experimental and validation side, is that, you know, it's a philosophical theory, and so it provides a framework, but not necessarily a falsifiable hypothesis, right? So, for example, there's a big debate right now in not specifically speech act theory, but other principles of pragmatics such as cooperation. Yeah, the whole Gricean idea that we are cooperative speakers. And there's been a huge debate in psycholinguistics about whether speakers are really cooperative. You know, because it seems that speakers are so prone to doing things in a fast, efficient, heuristic way that they sometimes won't pay attention to, you know, another person's model of the world, for example. So they'll talk as if the other person should know this, but the other person doesn't know this, right? And then, you know, there's a whole debate about whether these frameworks are really true, right? In these circumstances, I think I like to remind myself of what a philosopher once said. Richard Bach once said the whole problem with the way people talk about Grice, for example, but he could say this of Searle as well, is that people interpret them as if they're positing rules. They are not. They are characterizing processes. And then if you want a testable hypothesis, you have to figure it out. But that wasn't their job, right? So the answer broadly is yes, but.
Thank you. Any other question?
It was really interesting and motivating talk, as we were talking before. I was thinking now, regarding with Kees van Dinter and this last comment that you were doing, I was discussing with him about what he called the common ground. When he said, what is the knowledge that is common to all the people? So here you talk about the context, you talk about the purpose, but for me, one of the most difficult problem is that you have an algorithm and the input of the algorithm is the image, and you can look at the context of the image, but you need to think about the future, which is going to be used. Imagine when we are writing a paper, a technical paper, and we have to describe in a picture the result. If you think that this is going to be printed in color or in black and white, maybe the way how you represent the symbol is different. You are not making different with color. You have to look for different lines or whatever. So if you have your image that is very nice, you make a linguistic description, and later the people who is going to read your description and to take something with the image is looking at the image in a different presentation or in a context that is different, but you didn't know, you are not able to identify that. And also because sometimes there are implicit properties that are there that is not available in the given, it's not easy to identify at the beginning, but it's appearing later.
I agree. What I'd like you to clarify, though, is you said something about, you know, the future, like prediction. Are you talking about predicting the impact on the receiver?
No, I think that, of course, the way to have control under the experiment and is the information that you have here. But imagine that you have a problem, you have a many different pictures, you are generating a lot of text, but you don't know this tag test that you are putting in a database, for instance, in the future, who is going to use this test. So you are not generating the test thinking in the present, the audience, the expected audience of this text. So this has an effect also in the effectiveness of the sentence.
That is true. One of the things we, unless we do sort of explicit, for example, user modeling or something like that, where we're trying to have some kind of predictive model about how this will impact somebody of type A versus B versus C, right? When they're actually exposed to what the system's producing. Unless we do that, most of the time we're really thinking of a kind of default user, people who know something. Cases work with Roman Kutlak, for example, on Common Ground, right? What they were trying to do was use sources, online sources such as Wikipedia and so on, to try and figure out what is known about certain types of objects, right? So, you know, if you mention a person and they're quite famous, maybe because they're a pop star or movie star or something, right? Some things will be known and some things might not be known about them. And so the more something is likely to be known, and you can use these sources to sort of create some kind of probabilistic model of that, right? The more something's likely to be known, the safer it is to use, right? Because you can assume that your reader, your listener will know what you're talking about. But that only really works for the types of things which have a sort of public profile, if you like. Yeah. When we're talking about more specialized things, the sorts of things we often work on in our systems, or more, you know, just more common things, which you know, things like chairs and tables as opposed to movie stars. Yeah. It becomes much more difficult then to predict what the impact is going to be on of our choices, of the system's choices, on whoever's going to be hearing or reading this. Yeah. Yeah, I think your point is very well taken.
And there's a short question for ending. Alejandro, you're missing your opportunity of throwing back some questions public to Albert.
Please be kind.
Some people that's working now in ECG or monitoring people or patients. I have just one short question related with the deterministic algorithms, the incremental one or the greedy one. Are you aware of or other proposals in this regard, or finally this is more or less abandoned in order to go to the probabilistic ones?
Yes. So the incremental algorithm remains quite popular, and there have been many versions of it where its capabilities have also been enhanced. For example, to use Boolean. I didn't even go into that, but you know, things like negations or disjunctures and so on, plurals. But in general, I think yes, the general trend right now is for a move towards an increasingly probabilistic outlook. Not just in the kind of work I mentioned when I described, where is it? Oh well. Too far away. Never mind. When I described the pro algorithm, you know, there's that kind of work which is trying to kind of model choices in a stepwise fashion, but with a probabilistic perspective on making some choices more likely. But there's also work, for example, which is coming out now from the image and language, vision and language community, where they are doing, you know, trying to use, for example, object detections on images, figuring out what the properties of a particular object are in a quantitative fashion, and then probabilistically predicting whether this should be used in a description or not. The move is currently increasingly towards using probabilistic methods pretty much across the board.
Okay, thank you very much.